For our final part of our spectroscopy series, we're going to look at infrared spectroscopy. This is kind of the third piece of the puzzle, alongside mass spec and NMR, of methods that are going to allow us to determine the structure of organic molecules. Shown here is the electromagnetic spectrum, organized by wavelength, ranging from the longest wavelengths for radio waves to the shortest wavelengths from gamma rays. We have the wavelengths in centimeters, along with the energy for a mole of photons corresponding to these wavelengths, along with the molecular effects, that is to say, what the absorption of these types of electromagnetic radiation cause molecules to do. If you recall from mass spec, we saw that electrons could cause molecules to ionize and then fragment. It turns out that electrons have the same wavelength as X-rays. For an electron, since it's a particle, we call it a de Broglie wavelength, but X-rays and electrons share the same wavelength and energy for a mole of photons or electrons, and they cause ionization. We saw that radio waves in NMR could induce nuclear spin transitions. Today, we're going to look at how infrared light can cause molecular vibrations. And for this molecular vibrations, we're going to imagine a bond being analogous to two weights on a spring, and that spring can stretch or it can compress, and there will be therefore an equilibrium length of that spring. As that spring expands and compresses and expands and compresses, over time it will eventually reach an equilibrium length. We're going to imagine a bond acting that way, like two weights on a spring. So infrared comes from the word infra in Latin, which means below. So the word infrared basically means this is the region in the electromagnetic spectrum below red, meaning lower in energy than red. Of course, that corresponds to wavelengths longer than red, which basically is 0.8 micrometers to about 100 micrometers is the infrared region. In terms of where we look in this region, most bonds vibrate between 2.5 micrometers and 25 micrometers, and those correspond to energies of about 1 to 11 kcal per mole. Like we've mentioned, these energies that are absorbed by molecules will cause groups of atoms to vibrate with respect to the bonds that connect them. And those vibrational transitions, as those bonds vibrate in and out, correspond to distinct energies. So molecules will absorb those energies, and then they will re-emit them. And based on what frequencies are re-emitted, we can infer what types of bonds or groups are present on our molecule. So we've mentioned that the range of wavelengths that are absorbed by molecules ranges from around 2.5 to 25 micrometers. For the sake of reporting these numbers, it's more convenient to convert them into reciprocal centimeters, which we call wave numbers. So it's a simple conversion. We take the infrared wavelength in micrometers. We convert micrometers into centimeters. It's a factor of 10,000. There are 10,000 micrometers per centimeter. And then we invert those centimeters. So we have centimeters to the -1 power. And we call those wave numbers. An inverse centimeter, reciprocal centimeter, is a wave number. And this is useful for two reasons. First of all, it allows us to stop dealing with decimal numbers. For example, the difference between 4.1 micrometers and 4 micrometers might determine the difference between one type of bond and another. So instead of dealing with fractions of a micrometer, if we convert it into centimeters and then invert it, rather than dealing with 4 to 8, 4.1, 4.2, 4.3, 4.4, etc., we can deal with numbers from 1500 to 2500. So we can talk about 1550, 1600, 1625, 1610. We can easily distinguish between 1610 and 1615 rather than dealing with something like 7.4 and 7.35. So it makes the numbers a little bit more manageable. Also, remember that wavelength and energy are inversely related. A small wavelength corresponds to a big energy and vice versa. So by taking the reciprocal of the wavelength, it now means that a wave number is proportional to energy of the vibration. So a higher energy frequency, a smaller wave number, higher energy will correspond to a larger wave number. We have 4 micrometers corresponding to 2500 wave numbers, that's a higher energy, or 8 micrometers corresponding to 1500 wave numbers, that's a lower energy. So again, for 2 reasons, it makes the numbers easier to deal with, and it makes them proportional to the energy instead of being inversely proportional to the energy. So we're going to be using wave numbers to represent these vibrations. Here are some examples of the bond stretching frequencies, again reported in wave number. Generally speaking, like it says here, frequency decreases with increasing atomic weight. You'll see that as we go from a C bonded to an H, to a C bonded to a D, deuterium, to a C bonded to a C, as we get heavier atoms, our frequency decreases. Our energy goes down. These are lower energy vibrations from 420 to 350. And the wave number decreases, again, lower in energy from 3000 to 1200. You can also see that frequency increases with bond energies. So as our bonds get higher in energy, from a single bond to a double bond to a triple bond, again, more energy is embedded in these bonds as we increase the number of bonds. Our frequency also increases. We get more energy from 350 for a single bond to 611 for a double bond, for 840 for a triple bond. As our bond gets stronger, and the frequency increases as well, from 1200 to 1660 to 2200. Here we see that range for carbon-carbon bonds, single, double, triple. We also have those same similar ranges for carbon-nitrogen bonds, single, double, triple, from around 1200 to about 1600, 1650 to about 2200. Same for carbon-oxygen bonds. As we go from a single to a double bond, our energy increases, so does our frequency. So those are 2 trends. As our atoms get heavier, our vibrations slow down. That kind of makes sense. If you imagine 2 bowling balls on a spring versus 2 ping pong balls in a spring, if you flick that ping pong ball on a spring, it's going to vibrate very quickly. But if you push that bowling ball on the spring, it's going to vibrate very slowly. So the heavier atoms will correspond to lower frequencies. Also, as we get a stiffer bond, say a triple bond versus a single bond, as we get a stiffer bond, the vibration increases, the frequency increases. So again, imagine a loose spring as a single bond and a tight spring as a triple bond. If you flick those springs, the tighter spring is going to vibrate faster than the loose spring. Many molecules will have a wide range of vibration modes. We call vibrational modes. For example, if we look at water, water's got 2 bonds. You can imagine these different bonds stretching and compressing in different patterns. You could have symmetrical stretching, where both of the bonds are stretched and compressed at the same time. You can have asymmetrical stretching, where one bond is compressed and the other bond is extended at the same time, and vice versa. So one is coming in while the other one is going out, vice versa, going back and forth like that. You can also have a bending, or what sometimes calls a scissoring motion, where instead of the bonds extending and compressing, the angles are bending and twisting. These are called vibrational modes, different ways that the molecule can vibrate. And any molecule with n number of atoms will have 3n minus 6 vibrational modes. For example, water has 3 atoms, so 3n minus 6 would be 3 times 3 minus 6, so that would be 3 vibrational modes. These are the 3 vibrational modes for water. For methanol, for example, CH3OH, there are 6 atoms, so it would have 3 times 6 minus 6 equals 12 vibrational modes. And ethanol with 9 atoms would have 3 times 9 minus 6 which is 21 vibrational modes. So let's look very briefly at what these vibrational modes look like. This is from the LibreText's free version of the organic chemistry textbook. These are the three modes of water that I just showed you. This is the symmetrical stretch where the H's are stretching at the same time and compressing at the same time. This is the asymmetrical stretch where one H is compressing while the other H is stretching and vice versa. And this is that scissoring or that bending vibration. Those are the three modes of water. Here's carbon dioxide. Carbon dioxide has various other modes. We can have a symmetrical stretch where the O's are stretching and compressing at the same time. Also an asymmetrical stretch where we have one O compressing and the other O extending at the same time. We also have these bending modes for carbon dioxide. There's an asymmetrical bend. You can see that the C is kind of bending asymmetrically with the O's, and this is a symmetrical bend where the C is bending symmetrically with the O's. This is mentioning being inactive or being active. I'm going to mention what that means in a moment. But basically, because this is a nonpolar molecule and it's stretching symmetrically, it means that there's no dipole change, and that means it's not detective in IR. If it's an asymmetrical stretch, that means that there is a dipole change, and therefore it would be active in IR. Here are some other types of stretches or bends. This is for a CH2 group. So imagine we've got a carbon with two other groups, and those two other groups are going to be fixed in all cases. So this is how the H's are vibrating relative to the two other groups on the carbon. We could have a symmetrical stretching again where the H's are compressing and stretching at the same time. An asymmetrical stretch where one is compressing and the other is extending at the same time. We can have a scissoring where the H's are coming in and out, like that where the CHC bond angle is getting bigger and smaller. We can have a wagging where the two H's are coming in and out of the plane of these other two groups. So you see they're going in and out and in and out and in and out and in and out. We can have a twisting, which is basically an asymmetrical wagging where one H is coming out of the plane where the other H is going into the plane. So we can have that would be kind of like a twisting, and everything of course is happening relative to these other two groups that are remaining fixed in space. And then we can have a rocking. So we can have the H's kind of moving from one side to the other side. So these are 6 more vibrational modes. And you'll notice that the more atoms that we have in our molecule, the more possibilities we have for these vibrational modes. This is what an IR spectrum looks like. We have wavelength or wave number, so frequency on the bottom, ranging from 600 up to around 4,000. That's the typical range that we'll see. And remember that higher wave number is higher frequency, which is higher energy, and lower wave numbers would be lower frequencies and lower energies. So we'll tend to see lighter atoms and stiffer bonds up on the high frequencies, and we'll see heavier atoms and more floppy bonds in the lower frequencies. Remember that bonds will absorb infrared light at the same frequencies at which the bonds vibrate. On the y-axis is plotted the percent transmittance, that is to say, the percent of light that makes it through the molecule. And you'll notice that this is kind of like an upside down graph, because where we have low transmittance would be high absorbance. So it's kind of the opposite. We're looking at this graph kind of upside down. Way right here where we've got this big dip means that we've got low percent transmittance or high absorbance. So we've got bonds that are vibrating and absorbing at around 3,400. That turns out to be an OH bond stretching. We've also got absorptions around 3,000, which is a CH stretch. And we've got some other bonds way down here, which involve a CO stretch and some of these other vibrational modes like a CH3 rocking and a CH3 scissoring and an OH bending. We've also got some other combinations going on around 2,500. We'll talk about those a little bit later. So we've got this graph, and again, it's kind of plotted upside down. We're looking at the inverted peaks. Those low transmittance or high absorbance peaks are what we're going to pay attention to. Now, in the big picture of things, many vibrations on organic molecules are so ubiquitous, that means they are on almost every molecule, that they don't really have any way to help us distinguish one molecule from another. For example, the CH bending and stretching frequencies. Almost every organic molecule that we'll ever look at will have carbon-hydrogen bonds. So they will all have CH stretching, bending, rocking, twisting vibrations in their spectrum. Also, many of these vibrations overlap, and many can't be distinguished from one another in complicated spectra. For example, we've got a CH3 scissoring and an OH bending, and they're almost vibrating at the same frequency. It's very difficult to distinguish that there are two different frequencies there. So a lot of these things we can ignore. What we're going to look for the most part, are vibrations that are conspicuous. For example, our OH stretch, extremely conspicuous here, and a CO stretch, very conspicuous here. The fact that we have a CO stretch and an OH stretch are a good sign that we've got a C bonded to an O, and that O is also potentially connected to a hydrogen. You see that from 600 to 1400 is labeled the fingerprint region. This is the region in which most of the ubiquitous vibrations appear. Almost every molecule will have vibrations in this region, and that means that most of the stuff here is not able to give us any distinguishing information from one molecule to the next. But it is like a fingerprint in that every unique molecule will have a unique fingerprint region. So the fingerprint region is useful if you're comparing your spectrum against, let's say, a standard or a known spectrum. You can look at your fingerprint region and say, our fingerprint region is actually the same as the fingerprint region for molecule X. Therefore, we think our molecule is molecule X. So fingerprint region is useful for comparing one spectrum to the other, but it's not useful for giving us any specific information about what our molecule might have on it. All of our molecules are going to have CH stretching and scissoring and rocking. And some of them are going to have unique frequencies, like an OH bending, that gets blocked by these other frequencies. Certain vibrations on a molecule are what we call IR active, and certain vibrations on our molecule are what we call IR inactive. In order for something to interact with electromagnetic radiation, it must involve movement of electric charge. In NMR, we saw that electric charge was basically the spinning nucleus. In IR, it's no different. In IR, the movement of charge is within the bonds. So you can imagine if we've got a polar bond, as that bond stretches and compresses, the positive and negative poles of that bond move closer and farther away from each other. When they're far away from each other, we've got more charge. When they're closer to one another, they've got less charge. So as these bonds vibrate, they will be moving charge around, and that allows them to interact with the infrared light. So IR active vibrations will be in polar bonds or non-polar bonds if they are asymmetrical modes. So if we've got a non-polar bond, but it's stretching asymmetrically, that means that we're going to be moving electron distribution asymmetrically as that bond vibrates. All polar bonds will be IR active because no matter how we vibrate those bonds, the poles are going to move closer and farther away from each other, and that's going to change the amount of charge that is moving in that bond. So that means that IR inactive vibrations will be non-polar bonds that are vibrating in symmetrical modes. So sometimes if we've got symmetrical bonds that are non-polar, their vibrations will not interact with infrared light and they will not show up in the infrared spectrum. Here's what I mean by that. HF polar bond. You can imagine that as being two weights on a spring. One weight has positive charge, one weight has negative charge. As we bring those charges together, as the spring is compressed, there's going to be less overall charge as the dipole is decreased. The positive charge and the negative charge come close together and they become indistinguishable from one another. Their charges basically become zero as they overlap with each other. But as we stretch that bond, the positive charge and the negative charge get farther away, and now the negative charge is not as covered up by the positive charge, and vice versa. So we've got more charge. So we've got more charge when it's expended and less charge when it's compressed. So let's look at some of these bonds in red and decide whether these are active or inactive vibrations. Our first bond here, this is acetylene, C triple bond C. You'll notice that this bond is symmetrical from one carbon on the left to the one carbon on the right. This is a symmetrical bond, which means that its vibrations as this bond expands and compresses will do so symmetrically, and that will be inactive on IR. Here's a CH bond. Now, a CH bond is not polar, so normally we would think it would not be IR active. But since one side of the bond is different with the triple bond to a carbon, then the other side of the bond is just a hydrogen. That means that it's an asymmetrical stretch. As this molecule stretches and compresses around this bond, the electron distribution will change. We've got more distribution on the left than the right, and as we bring them together or bring them farther apart, the overall distribution across the whole molecule will change. So that's an asymmetrical stretch, and that will be IR active. Here's a C triple bond C. It's a symmetrical bond, but we've got a group CH3 on one side and an H on the other side that are not equal. As this bond stretches and compresses, it will do so asymmetrically. So that will be active. Here we've got an inactive bond because, again, it's symmetrical on both sides. Here we've got an active bond because it's asymmetrical, a triple bond on one side and a CH3 on the other. Ethane's carbon-carbon bond would be inactive because it's symmetrical. Methane's CH bonds would be active because they're asymmetrical, the carbon on one side with the methyl versus the hydrogen. 2-butene would be symmetrical. This is a symmetrical bond, so it would be IR inactive. But the double bond would be inactive, but the single bond would be active. These carbon-carbon bonds would be active. They've got 3 hydrogens on one side and the C double bond C on the other side. Here's propene. Propene's carbon-carbon double bond would be active, whereas butene's would be inactive. Again, because this is asymmetrical. We've got a methyl on one side and hydrogens on the other side. Let's look at some spectra of hydrocarbons and the type of frequencies that we can expect to see. We saw this earlier in our table that carbon-carbon bond stretching frequencies will range from 1200 when they are single bonds to around 1650, 1660 when they are double bonds to slightly less than 2200 when they are triple bonds. And again, these are wave numbers. The carbon-carbon single bonds are in the fingerprint region. The fact that we see vibrations at 1200 doesn't mean a whole lot. But seeing vibrations at 1660 or slightly under 2200 are going to be unique to certain molecules. If we see those vibrations, we can go, aha, we've got a carbon-carbon double bond or a carbon-carbon triple bond. That's interesting. A carbon-carbon single bond is not interesting. So we would call that the fingerprint region. Again, higher energy or stiffer bonds will vibrate at higher wave numbers. So that's why the double and the triple are higher in energy and frequency. Now, for double bonds, they actually show up in a specific range. Here, let's look at these 3 cyclohexene rings. We've got cyclohexene, we've got cyclohexadiene, and benzene, or kind of cyclohexatriene. An isolated carbon-carbon double bond, a double bond just sitting all by itself, will tend to be between 1640 and 1680 wave numbers. We're going to say we'll split the difference. The book's going to say 1660 wave numbers. But a conjugated carbon-carbon double bond, like these guys in the diene, these are conjugated, alternating double, single, double. That's a conjugated system. Notice that that goes down from to about 1620 to 1640. And as we go to an aromatic system, the vibrations of those double bonds go all the way down to 1600. These are distinct regions, which means that we can now differentiate between an isolated double bond, a conjugated double bond, and an aromatic double bond. Now, why is it doing this? Think about benzene. Remember that there are two resonance structures to benzene. One of them has the double bonds where they are placed currently, and the other resonance structure has the double bonds move to where the single bonds currently are. So this double bond would move there, this double bond would move there, and this double bond would move there. The fact that those two resonance structures are equivalent means that each of these bonds is not really a double bond, and each of these single bonds is not really a single bond, but rather each double bond is really 1.5 bonds, and each single bond is really 1.5 bonds, because in one structure it's a single bond, in the other structure it's a double bond. So the average between the two structures would mean that all of the bonds in benzene are 1.5 in order. Well, 1.5 is between one bond and two bonds. So as we get more conjugated from a conjugated system to an aromatic system, our double bonds start to look more like single bonds. So our pure 1660 double bonds start to go down in frequency, down to 1600, because they start to look more like single bonds. These conjugated bonds are more single bond-like than the isolated double bond is, but they are not quite as single bond-like as the aromatic double bonds are. So keep that in mind. The more conjugated a system is, the more single bond-like its double bonds are, and so the lower frequency they will vibrate at. We can also differentiate in IR between sp3 hybridized carbon-hydrogen bonds, sp2 hybridized carbon-hydrogen bonds, and sp hybridized carbon-hydrogen bonds. Remember that sp3 hybridized bonds have 1/4 S character. They are 75% P character, meaning that they are more elongated. And as we go from sp3 to sp2 to sp, we increase S character, decreasing P character, which means that these bonds get shorter. We saw that when we looked at our alkene and alkyne chapters, that the carbon-hydrogen bonds get shorter as we increase S character. That means that their vibrations are going to get faster. Again, imagine a long floppy spring versus a short tight spring. As we increase S character, these bonds get shorter and tighter, and so their frequencies vibrate faster as well. So we'll see carbon-hydrogen sp3 bonds from 2800 to 3000. We'll see sp2s from 3000 to 3100, and we'll see sps from 3300, a little bit higher than that sometimes, and that'll be a sharp peak. So these are distinct. And again, these are specifically the carbon-hydrogen bonds. So we can see the single bonds, the carbon-carbon single bond, or the carbon-carbon double bond, or the carbon-carbon triple bonds, again, 1200, 1650, 2200. We can also see the corresponding hydrogen bonds if they're there. If we have a terminal alkyne, we will see this sp hybridized carbon-hydrogen vibration. But if we have an internal alkyne, that hydrogen won't be there. That'll be a carbon instead, and we won't see that bond. So that can even help us determine whether a double bond or a triple bond are internal or terminal. So let's look at some examples of these hydrocarbons. This is hexane. Remember when we looked at the mass spectrum of hexane, we kind of used it as a baseline. We used it to look for common alkyl fragments. What does an ethyl group look like? What does a propyl group look like? What does a butyl group look like? What does a pentyl group look like? Well, we can use hexane again as an alkane baseline in IR, meaning that if you only have alkanes, this is what your spectrum will typically look like. This is your baseline. You'll see CH sp3 stretching from about 2800 to 3000. Again, that's what we saw here. Our sp3 hybridized bonds will show up from 2800 to 3000. This peak right here is very typical. As long as you have some sp3 carbon-hydrogen bonds, you will see this peak in your spectrum. You will also see these corresponding CH bending frequencies, but again, this is in the fingerprint region, so you'll typically tend to ignore things below 1400. This is a baseline for hydrocarbons. Now, if we go from hexane to one hexene, that is to say, a terminal alkene, we should see two new bonds appear. We should see a CC double bond. Now, this is an isolated double bond, so this should be at the higher end of our carbon-carbon double bond vibration range. We see a CC double bond stretch showing up here at 1640. That peak is absent in hexane. It is present in one hexene. So that's something different from our baseline. We also see a new peak emerging slightly above 3000, close to 3100, and that is our sp2 hybridized carbon-hydrogen stretch. So comparing our one hexene to our hexane, we should see two unique vibrations corresponding to a terminal alkene, the carbon-hydrogen sp2 stretch and the carbon-carbon isolated alkene stretch. So here's one hexene again. I just moved it up. So we compare it to cis 2-octene. Here's cis 2-octene. And again, it should look pretty similar. We've still got a carbon-carbon double bond that's showing up at 1660. And we've got a carbon-hydrogen sp2 bond right here. These sp2 hybridized carbon-hydrogen bonds showing up at 3000, a little bit over 3000. 3020 versus 3080, but you can see that these are really similar. The vibrations might be slightly stronger or slightly weaker. For example, the carbon-carbon double bond here is a stronger peak. The carbon-carbon double bond here is a weaker peak, and they might differ by 10 or 20 wave numbers, but for the most part, all the functional groups are here. The point that I want to make here is that IR spectra tell you what are present, what types of bonds are present, or what types of groups are present. It can't tell you how many there are. For example, if we've got 2 carbon-carbon double bonds or 3 carbon-carbon double bonds, if they've got the same properties, they're going to show up in the same place in the spectrum. And it also doesn't tell us what is connected to what. It does not tell us whether this is, for example, cis or trans 2-octene. Or maybe this could be a 3-octene or a 1-octene. It can be very difficult to tell that in an IR spectrum. On the other hand, that information is very easy to obtain by NMR. So each of these different spectroscopic methods give us a different piece of the puzzle. IR is very good at telling you what we have. NMR, sometimes it's hard to tell what we have. For example, it's easy to tell an aldehyde or a carboxylic acid in NMR, but it's hard to tell if we've got a double bond that's internal or terminal in NMR. It can be much easier to tell that in IR. Here's 1-octine, a terminal alkyne. So here we should see our normal hexane baseline, but we should now have a carbon-carbon triple bond, and we should have a carbon-hydrogen sp2 bond. So here's our carbon-carbon triple bond. Again, that's slightly below 2200. This is 2119. That's our C triple bond C stretching. And then we've got at around 3300 a CH sp hybridized stretch, a stiffer sp hybridized stretch. When we compare 1-octine, our terminal octine, to 4-octine, which is not only an internal alkyne, but it's a symmetrical alkyne. Notice that in 4-octine, we've got the same thing on one side of the triple bond as we have on the other side of the triple bond, which means that this is now an IR inactive alkyne. We do not see its vibration. The 2119 peak is gone. And since this is an internal alkyne, we don't have the sp hybridized CH bond. So that vibration is gone. And the result is that 4-octine spectrum looks an awful lot like hexane spectrum. We don't have anything that's different from our normal alkane baseline. If you pay close attention, you will see that the fingerprint region does look quite different. Here's the fingerprint region for 4-octine. We can compare that to the fingerprint region for hexane. It's quite different. Here's hexane. Here's 4-octine. So if you were to go and look up a reference for your spectrum, you think, okay, maybe I've got 4-octine, and you look it up, the fingerprint regions should match. But you would not be able to tell that this is 4-octine just by looking at its fingerprint region and nothing else. So that is a bit of a buyer beware, a caveat. Be aware that there are some things in IR that you might not see, and it can be easy to be misled to believe that your spectrum refers to something that it doesn't. Of course, mass spec could tell you that. Based on the molecular weight, you would clearly be able to tell that this is not hexane. 4-octine would have a different parent peak than hexane would. Also in NMR, you would see a different splitting pattern in hexane than you would for 4-octine. So here's a spectrum. Let's figure out if this is an alkene, an alkane, or an alkyne. Well, try to remember what our baseline looks like. There are a couple of conspicuous peaks here that are not in our baseline. We've got a peak here at around 16, maybe 1640. And we've got a peak here kind of jutting out just above our 3000 range at about 3050, 3050, maybe 3100. So this is an alkene. We don't see our peak a little bit below 2200, which you would expect for an alkyne. And we don't see anything up at 3300, which you'd expect from an sp hybridized carbon hydrogen. But we do have the sp2 hybridized carbon hydrogen bond here at 3100, and we have a carbon-carbon double bond a little bit above 1600. So this is an alkene. Spectrum B, alkane, alkene, or alkyne. Well, this is clearly an alkane. This is exactly what our baseline looks at. We've got the CH sp3 stretching. You've got the CH bending in the fingerprint region. We've also got some carbon-carbon single bonds here. Looks like at around 1400. This looks like a plain old alkane. Nothing fancy. Now this spectrum is quite interesting. Again, spectrum C, alkane, alkene, or alkyne. Well, this is weird. Notice that we are almost completely missing our peak at 3000. This is part of our baseline that's now gone. But we have a very strong peak at around 3300. And that's what we would expect for a sp hybridized carbon hydrogen bond. So this appears to be an alkyne with a terminal carbon hydrogen triple bond, sp hybridized carbon hydrogen bond. We've also got a little peak at around 2200. That's got to be our carbon-carbon triple bond. The fact that we've basically got no alkane signals at 3000 makes me think that this is acetylene. This is C triple bond C with two hydrogens on it, which have no sp3 carbon hydrogens and no sp3 carbon carbons. So that's kind of a weird spectrum, but we do have our conspicuous alkyne carbon-carbon triple bond and sp hybridized carbon hydrogen bond. Other functional groups to look for. Alcohols have broad peaks that are centered around 3300, the OH frequency. Carboxylic acids, we will see their OH peak broad around 3000. So broad like an alcohol, but a little bit lower frequency. And amines show up kind of the same place that alcohols do, but they will have spikes within their peaks. I'll show you what those spikes look like in a moment. These are other conspicuous frequencies from common functional groups. Here's an alcohol. That broad peak centered around 3300. That's dead ringer for an alcohol. Here at 3000, we've got our typical baseline alkane signals, our sp3 hybridized carbon-hydrogen stretches. We've got in our fingerprint region the carbon-oxygen single bond, if you recall, that's around 1200. But again, that's in the fingerprint region, so that's a not reliable peak. That peak could be coming from lots of other things, depending on what's going on in the molecule. But basically, if we ignore anything below 1400 and only look at things above 1400, all that we can tell is we've got an OH and an alkane. This turns out to be one butanol. We see our alkanes and our alcohol. Here's dipropylamine, two propyl groups on a nitrogen. Again, we've got the normal alkane signals from our propyl groups. So we'll see our saturated CH stretches around 3000. We see kind of the same thing going on in the fingerprint region. Notice that we have a CO stretch, again, here at around 1000 to 1100. We've got similar things going on here. That's why these are not reliable things, because if you look at this and say, oh, this must be a CO stretch, it's actually not. So don't put too much credence in anything below 1400. But here we've got kind of a broad peak going on around 3300 with a spike here. I'm going to show you another example later on that has these spikes. Those spikes come from basically inversion of the amine. We'll talk about, when we learn about amines, we'll talk about their geometry and how they can invert. That's what those spikes are coming from. Other things we'll tend to see, ketone carbonyls show up around 1710. So you'll see that right here. It's a very sharp peak, 1718. Aldehydes, you'll see our carbonyl a little bit higher, 1725, as well as a very specific CHSP2 stretch at 2700 to 2800. Remember before, our sp2 hybridized carbon-hydrogen stretches were at a little bit above 3000 when they were part of an alkene. But when they're part of an aldehyde, this carbon-hydrogen stretch, we see two vibrations at 2700 and 2800, and our carbonyl is a little bit higher frequency. For an acid, notice that the carbonyl is actually the same as it is for a ketone, the 1710 in both cases. But with an acid, we'd additionally see the broad acid OH vibration that is centered around 3000. So they say this can be basically start at 2500 and end at 3500, centered around 3000. So that's why it's easy to tell a ketone from an aldehyde from an acid. When you're looking at NMR, it can be kind of difficult to tell, say, an ester from an ether. But the ester, you would very clearly see a carbonyl stretch that you wouldn't see from an ether. So IR can tell you important information that is often ambiguous in NMR. Here's 2-heptanone. This is a ketone. So we've got a carbon double bond O, our very strong stretch, 1718. It's not quite as high as our aldehyde would be. And we're also missing pieces around 2700 and 2800. We don't have anything in those regions here. So this is not an aldehyde carbonyl. It must be a ketone carbonyl. We also don't have the acid, broad acid peak from 3500 down to 3000. So this is very clearly a ketone. Something that's very interesting that you often see in carbonyls are what are called overtones. I don't know if any of you are musicians, but if you are, or you've ever played a piano, if you take a well tuned piano and you hold down the sustain pedal and then you hit one note very hard, you say hit middle C really hard with the sustain pedal. If your piano is perfectly tuned or very well tuned, you will hear other strings in the piano vibrating alongside your middle C that you hit. Those are called overtones. It turns out that multiples of your vibrations will be incident by the vibration of your principal frequency. So if you hit middle C, it might also vibrate the C strings below and above at certain mathematical ratios. Those are called overtones. We see the same thing in IR. Often what we'll see from ketones, since ketones and aldehydes, these carbonyl frequencies, happen right in the middle of our spectra, we will tend to see multiples of those vibrations on our spectrum. So where we would see 1718, we see overtones at around 3400, the multiple of that. So sometimes you'll see these overtones. They can be ignored. If you say that looks really weird, think about the fact that there might be something else that's causing that vibration. Basically, these carbonyls are causing other bonds to vibrate at multiples of their frequencies. Here's butyraldehyde or butanal, the 4-carbon aldehyde. We should now see a higher frequency carbonyl stretch, which we do. This is now 1724. We see our aldehyde CH stretch at 2700 and 2800. These additional peaks right here showing up just below our normal alkane stretch, our baseline. That's our aldehyde CH stretch. And we have again seen an overtone, a 3400 overtone that's a multiple of the 1700 carbonyl stretch. More functional groups. Here's a carboxylic acid. This is hexanoic acid. So we should see our normal hexane vibrations. Notice that the OH stretch, the acid OH stretch, that's so broad from 2500 ranging all the way up to 3500, centered around 3000. Notice that almost blocks out our CH stretch altogether. So that's another buyer beware, a caveat that sometimes these signals will occlude other signals. For example, if we had some small signal around 2500, that might be blocked off. We might not see aldehyde peaks, our 2700 and 2800 aldehyde peak, if there's also an acid on our molecule. So be aware of that. Just because you don't see it doesn't mean it's not there. That's one unfortunate side effect of some of these functional group stretches and other frequencies, is that they will block others. But we've got our carbonyl, that's again in our ketone range, 1710 approximately 1711. This is very clearly an acid. Like we've mentioned before, resonance delocalization of a double bond will lower its frequency or wave number because it makes double bonds more single bond-like. This double bond here, the carbon-carbon double bond, there is a resonance structure in which that carbon-carbon bond is only a single, which means that it's not going to be a pure double bond. It's going to be lower than it would be more towards the single bond range. Same thing with this carbonyl. This carbonyl normally we would expect it to be, if it's a ketone, we'll say 1710. But because that ketone has a resonance structure where it's a single bond, the single bond would be about 1200. So this is lower than 1710 at 1685. More single bond like. It's also more lower energy. So again, energy corresponds to wave number. Higher energy is higher wave number, lower energy is lower wave number. Resonance delocalization makes something more stable, lowers the energy, gives a lower wave number. So notice that all of these ketones here, or all of these carbonyls here, are conjugated. This ketone is conjugated with the alkene. That lowers the frequency of the ketone. Here's an aldehyde, normally 1725, is lowered because it's conjugated with this double bond, 1690. Our acid, again, normally around 1610, is lower, 1687, because it's conjugated with the benzene ring. Notice that these are now more difficult to discern. 1687 for an acid, 1690 for an aldehyde, 1685 for a ketone. Now they're very difficult to discern, so we might need other information alongside of that. For the aldehyde, again, we'd see this 27-2800 CH stretch. And for the acid, we'd see the OH stretch. So a lot of times the carbonyl is not the defining frequency from these functional groups. Same thing with a nitrogen for an amine. Normally this ketone again would be 1710 for that carbonyl. But if it's an amide with the nitrogen next to it, that nitrogen is a very strong resonance donator. That N is very willing to donate its electrons into that carbonyl, which gives this carbonyl significant single bond character. That is to say that for the amides, the structure on the right here is a predominant resonance structure. This gets shifted from 1715 all the way to 1640 to 1680. So much lower than any of this other conjugation does. N is a strong resonance donator. So here's an amide, C double bond O, where the carbon bearing the double bond O has an N on it. We've got our CH stretches, our baseline, those are here, nothing surprising. Here's our broad peak from around 3300 with our two spikes. See those spikes there? That is typical of NH groups, which is our nitrogen group here. Since that nitrogen is on the carbonyl though, we end up with a very low carbonyl peak. Now again, beware, because this 1630 to 1660, that's also our alkene region. Alkenes show up in that region, whether they are isolated or conjugated, will be between 1630 and 1660. So it can be a little bit ambiguous. It's hard to tell, for example, that this is an amide and not an alkene with an amine somewhere. So be aware of that. It's a little bit ambiguous here. Esters shift things the other direction. The C double bond O peak on esters shift above 1715. We get 1735 or 1738 or 1785. Notice that when the ring is cyclic like this, it goes up to 1785. Now, why? Well, O is more electronegative than nitrogen, so it has less proclivity to generate resonance by donating electron density into that carbonyl. It does not do it nearly as much as nitrogen does. That is to say that the CO therefore has more double bond character, and so it's going to be stiffer and have higher energy, higher frequencies. Notice also that the strained ring, this four-membered ring, moves the peak even further up. What happens is because this ring is strained, these CH2 groups on either side of the carbonyl are closer to each other than they would like. They are also closer, therefore, to the carbon, and that increases density at the carbonyl and makes the bonds differ as well. So there are some very fine ways to determine what's going on in our structure if you are paying close attention. Carbon-nitrogen bonds show up approximately in the same regions as carbon-hydrogen bonds. CN single bonds are 1200, CN double bonds are 1660, CN triple bonds, remember that CC triple bonds are a little bit below 2200. CN triple bonds are a little bit above 2200. So you can differentiate between those pretty easily. The CN signals are usually quite strong, meaning that they have low transmittance and they tend to be very narrow, so these very strong peaks. So here we see something at 2250 That's a little bit above 2200, and it's pretty strong. Normally, we would see triple bonds would be below 2200, and they were moderate or weak. When we looked at alkynes, those were smaller peaks. So this is butyronitrile, a 4-carbon chain with a carbon-nitrogen triple bond. We should see nothing other than our background alkane signals, but we're going to add a carbon-nitrogen triple bond at around 2250, a strong peak a little bit above 2200. So to break this down, our regions are actually quite simple. Our fingerprint regions will tend to be our heavy atom single bonds. That's what show up in our fingerprint region, and usually we can ignore those. Almost everything will have carbon-carbon single bonds. Not everything will have carbon-oxygen single bonds or carbon-nitrogen single bonds, but those signals are unreliable. There are many other signals that show up in the same place and can block or add to or be in that location that are not these bonds. So you can ignore the fingerprint region for the most part. From 1600 to 1800, we have carbon-carbon double bond, so alkenes, and remember those can change depending on whether they are isolated or conjugated or aromatic. We've got carbon-oxygen double bonds, and those can change depending on whether they are ketones or aldehydes or whether they are conjugated or not. Same thing with our nitrogens, our carbon-nitrogen double bonds. Those will be in this region. They will tend to be stronger peaks, and again, they can change depending on whether they are conjugated or not. We've got our triple bond region. Carbon-carbon triple bonds will be a little bit below 2200, and they will be moderate or weak. Carbon-nitrogen triple bonds will be a little bit above 2200, and they will be usually strong. And then we've got our light atom regions. So carbon to hydrogen, oxygen to hydrogen, and nitrogen to hydrogen. Remember what those were. For carbon, if it was sp3, it was 3000. If it was sp2, it was around 3100. And if it was sp, is around 3300. The OH was broad, whether it was centered around 3300 for the alcohol or centered around 3000 for the carboxylic acid. And the nitrogen tended to be around 3300, not quite as broad as the alcohol, but also including spikes. So within these regions, this is where you look, and then depending on what it looks like within this region, you can determine what the context of these bonds are. Your book also has a table to summarize what we just said. Now that's all for IR. I want to take a very quick look at X-ray diffraction. We're not going to be doing any X-ray diffraction, or we're not going to be interpreting X-ray diffraction spectra, but X-ray diffraction is a very important method that was used a lot early on in spectroscopic experiments and has played an important role in the history and discovery of how chemistry works. So the principle with X-ray diffraction is that electrons will scatter electromagnetic radiation. So if we've got an electron, recall that I said earlier, electrons and X-rays have the same approximate wavelength. X-rays, we would call it their wavelength. For electrons, we call it a Broglie wavelength. But regardless, they vibrate at approximately the same frequencies. So if we have incoming X-rays bombard an electron with X-rays, it will absorb those X-rays and will also cause them to scatter. So some X-rays will pass through unscattered, but some X-rays will deflect. And as the X-rays deflect, it will cause the electron to move. You notice that as we deflect, the greater the incident of those deflections, the more our electron moves. It will deflect them that way. It will also deflect them that way. And as our electron moves up and down, it will vibrate. And as we have a vibrating charge, remember electrons are of course charged, that vibrating charge will emit electromagnetic radiation, and we can detect that vibration. So here's how it works. Imagine that you've got two electrons that are vibrating, and kind of like two stones that you throw into a pond. Those vibrations will cause ripples. So notice that this pink electron is causing ripples to emit from it, and this electron is causing ripples to emit from it. But notice that where these vibrations, these ripples overlap, do you see how we get these light and dark patterns, these banding effects as these ripples overlap? You see that light, dark, light, dark, light, dark, light, dark. Here we've got dark, light, dark, light, dark, light, dark, light. Those are interference patterns between the two vibrations of these electrons. If you trace those interference patterns out, like we did with these yellow lines, if we trace those vibrations, those interference patterns, notice that they end up, all of those lines trace back directly in between those two electrons. So you can use these interference patterns to determine the midpoint between two bodies that were causing those interference patterns in the first place. You can therefore use this, since atoms have electron density around them, you can use X-rays and X-ray diffraction to infer on a molecule where the atoms are located. And that will tell you the shape of the molecule, and from that you can infer how the atoms are attached. X-rays were discovered in 1895 by Wilhelm Röntgen. The story is that he had a candy bar, a piece of chocolate, in his pocket, and he walked by a source that was emitting X-rays in one of his labs and noticed that the chocolate melted when he walked in front of it. This is the first X-ray that was ever taken. He noticed that when he put his hand behind a panel that was being bombarded with X-rays, he could see the image of his bones in this shadowy projection onto the screen. This is a picture, an X-ray of his wife, Frau Röntgen, and her hand. You can see the wedding ring on her ring finger. In 1912, Max von Laue invented X-ray diffraction, which is what we've talked about, which is where you bombard a sample with X-rays, and the X-rays will cause the electrons to vibrate, and it will also cause the X-rays to diffract. And if you look at that diffraction pattern, you can infer the structure of your molecule. This was a diffraction pattern of copper sulfate taken in 1912, the first X-ray diffraction of a molecule that was ever taken. William Lawrence Bragg was the first to determine the structure of something from von Laue's X-ray diffraction pattern. He actually discovered the structure of zinc sulfide from a diffraction pattern taken from Max von Laue's experiment. He did that in 1912, and he won the Nobel Prize 3 years later for it. In 1915, he was the youngest Nobel Prize laureate ever. And you're probably familiar with this famous X-ray diffraction pattern. This was taken of DNA by Rosalind Franklin in 1952 and confirmed the double helical nature of DNA. In 2000, the complete structure of the large ribosomal subunit of the ribosome was discovered by X-ray diffraction by a professor named Thomas Stites, who was at the time, and he still is, working at Yale, which is where I went to grad school. There's an article on Wikipedia that mentions that he won the Nobel Prize in 2009, which is when I was there. It was pretty cool to be in the department of a Nobel Prize winner. They discovered, like we said, the structure of the large ribosomal subunit by X-ray diffraction, which was 100,000 atoms, not including hydrogens, 25 nanometers across or 250 angstroms across, greater than 100,000 atoms, not including hydrogens. And they discovered the position of every atom in this ribosome from using X-ray diffraction, an incredibly difficult and long and laborious process to do it with X-ray diffraction and have it confirmed by all other methods possible. An incredible achievement in science. So that's the end of our IR spec lecture. For workshop, we're going to do practice problems on the board, and we're going to start thinking about how we can combine information from mass spec, from hydrogen NMR, from carbon NMR, and from IR, and put the different pieces of the puzzle together to have a bulletproof defense of a structure based on the spectroscopic evidence.